Question 10.73. A 100 kg uniform bar of length L equals 5 meter is attached to a wall by a hinge at point A and supported in a horizontal position by a light cable attached to its other end. The cable is attached to the wall at point B at a distance D equals 2 meter above point A. First part of the question is asking us to find the tension T on the cable. And in the second part, we need to find the horizontal and vertical components of force acting on the bar at point A. So here in this question, you have a uniform bar that has a mass M of 100 kg and the length of the bar is 5 meter. The bar is attached to the wall with the help of a hinge at point A and it is supported by the cable which is attached to the wall at point B. Distance of point B and A is equal to D, which is 2 meter. And we need to find the tension in the cable. Now, since the bar is not moving, it is in a state of static equilibrium. And to be in static equilibrium, the net forces acting on the bar must be equal to 0, as well as the net torque must be 0. So I'm going to write for the bar net torque equals 0. Now, before we discuss this further, let us first understand all the forces producing torque on the bar. The first force is the force due to gravity Fg, which is directed vertically down from the center of gravity, which is at the same point as the center of mass. And then you have the tension in the cable T. Since the force due to gravity is pulling the bar downward, it produces a torque which is clockwise, whereas the tension in the cable will produce a counterclockwise torque. If you want the net torque to be 0, this means that torque which are counterclockwise must be equal to torque which are clockwise. Now, how do we calculate this torque? You can find the torque tau as Rf sine theta, where F is the force producing the torque, R is the distance of that force from the axis of rotation, and theta is the angle between them. So for counterclockwise torque, the force producing this torque is the tension T, and the point of application of this force is at the other end of the rod, and distance of this point from the axis of rotation is the length of the rod. Let us call this distance as R1, and we write R1 to be equal to L, and the tension T makes an angle theta with the bar. Clockwise torque is produced by force due to gravity Fg, and this force is at a distance, let's say R2 from the axis of rotation. Since force due to gravity is acting at the center of mass, this distance R2 will be equal to the position of center of mass, which is L by 2. Fg is making an angle of 90 with the bar because it is perpendicular to the bar. So we can write for counterclockwise torque as R1t sine theta equals clockwise torque will be R2 Fg sine 90. We need to find the tension in the cable, so let's rearrange the term. I will write tension T as R2. Fg we can write as M into G. Sine 90 is 1 over R1 sine theta. Now let's substitute for R2 and R1. R2 is L by 2, M times G over R1 is L sine theta. Now we can cancel off the L over here, or you can just substitute the value of L to find your answer. But before we substitute, I still need to find what is the angle theta. Now theta is not given to us, but we have the sides which are opposite to the angle theta and adjacent to it. So to find theta, I can use any of the trigonometric ratio. Since we have the opposite and adjacent side, I'm going to use tan theta. We know tan theta is opposite side over the adjacent side. In our situation, opposite side is D, adjacent side is L. So theta will become equal to tan inverse of D over L. So we write this as tan inverse D is 2 L is 5 and theta will be equal to 21.8 degree. Now let's substitute everything in our expression for t here. We get t to be equal to L is 5 meter by 2. Mass of the bar is 100 kilogram. Acceleration due to gravity is 9.81 over L again is 5 into sine 21.8. And then when you solve this, you get tension T to be equal to 1320.8 Newton. Now let's discuss part B of the question. In part B, we need to find the horizontal and vertical component of force acting on the bar at point A. Now, since the bar is attached to the wall and it is not free to move, the wall will exert forces at point A. One of the force which we call the horizontal force, I will write this as FH. This FH is pointing away from the wall and it is usually the normal force that the wall exerts on the bar. And then you have the vertical force which we will call as FV. And this FV is usually the force of friction that prevents the bar from sliding down. And in this part, we need to calculate what are the values of these two forces. Now we know as the bar is in static equilibrium, one of the conditions for static equilibrium is the net force acting on the bar must be equal to 0. That means vector sum of all forces along x-axis must be 0 and vector sum of all forces along y-axis must also be 0. So let us understand all the forces acting here before we continue with this. Like we discussed before, we have the force due to gravity Fg acting vertically down. And then we have the tension in the string. This tension is making an angle theta with the bar. And this theta we found in the previous problem to be 21.8 degree. Since the force of tension is making an angle with the horizontal, we can split this force into its component. One component that will go along the x-axis, which we call as t cosine theta, as this component is attached to the angle theta. The other component that goes along y-axis, which we call as t sine theta. So these are all the forces acting on the bar. And now let us use the equation of net force to calculate their values. We will begin with forces along the x-axis. I write F net x to be equal to 0. Now F net x is the vector sum of all forces acting along x-axis. We have two forces along x-axis, FH, which is the horizontal force pointing to the right, and t cosine theta pointing to the left. So we can write this as FH minus t cosine theta equals 0. So while writing these forces, we use the sign convention. All forces going to the right or going up will be taken as positive, whereas the one going to the left or going down will be taken as negative. So let's rearrange the term. I get FH to be equal to t cosine theta. Tension T we found in the previous part as 1320.8. Cosine of the angle 21.8. That gives me the horizontal force to be equal to 1226.3 Newton. Then we do the same thing for forces along the y-axis. We write F net y to be equal to 0. Again, F net y is the vector sum of all forces acting along y-axis. Along y-axis, we have three forces. One is the vertical force Fv. Then we have the force due to gravity Fg pointing down. And then we have t sine theta pointing up. So we write this as Fv plus t sine theta minus Fg to be equal to 0. Let's rearrange to rewrite in terms of Fv. Vertical force Fv will be equal to Fg minus t sine theta. Fg we can write as m into g minus t sine theta. Now let's substitute. We get Fv to be equal to mass of the bar is 100. G is 9.81 minus the tension T is 1320.8 into sine of the angle 21.8. And when you solve this, you get F vertical to be equal to 490.5 Newton.